Good day everybody. So today I'm going to give lectures on stability of metal complexes on 18 electron rule. 18 electron rule basically refers to a complete filling of metal valence shell. It has 3 orbitals, S, P and D. If all these 3 orbitals are fully filled with electrons, we say that the metal has achieved the effective atomic number, ion, of a normal gas, or in other words, has obeyed ion rule. So those metals or metal complexes that have achieved this ion rule can be said to be a stable complex. How do you count this number of electrons? It's very easy. Yeah? To count this number of electrons, you just need to know the number of electrons balanced on M, then you add the number of electrons contributed by each ligand. It's only two things there. But of course, if the complex carry a positive charge, the total number of electrons need to be deducted by the number of charge. Otherwise, if the complex carry a negative charge, the total number of electrons needs to be added by the number of charge. Alright. So, electron valence and electron contributed by ligands can be simply determined through these two things. Once, electron valence on M, you can just simply get it by the group number shown in the periodic tables. Of course, for electron contributed by ligand, there's no other way to do it. You need to memorize. You need to memorize. So for M, for example, on electron valence on M, if you refer to the periodic tables, you will see there is a group number. So this group number, for example, like scandium, group 3, the titaniums, group 4, group 5, 6, 7 onwards. These numbers refer to the electron valence on M. So you can get that number straight away from the from the periodic tables. While for ligands, there is no shortcut, you need to memorize. This is just examples of the possible ligand that attach to metal in metal complexes. This is the number of electrons that it can contribute. Here, for example, the normal one, like CO, the carbonyls. Carbonyls, it contributes two electrons. Chlorine, bromine, or iodine, they contribute only 1. So it's contributed by each ligand. Let's take an example. So we have this molybdenum with 6 carbonyls. So you want to know how many electrons or how many valence electrons around MO in these metal complexes. So we have MO, the metals from group 6, so it's 6 electrons. Alright? And CO, you know, CO contribute 2 electrons. But we have 6 CO. So it's 2 electrons times 6, it's 12. So the total number of electrons is 18. So it has obeyed ion rule. This is another example. Alright, we have different type of ligands, and then we have metals. Now the metal is iron. So iron is from group 8, so it's 8 electron. Now CO is 2 electron, but there are 2, so 2 times 2 is 4. Then chlorine, or the chloro group, is 1 electron contributed by chlorine, while this is what we call cyclopentadienyl. It contributes 5 electrons, and the total up, when you total this up, you will get 18 electrons. So contributed by the metal plus what contributes by the ligands. Right. This is another example, vanadium, right? But this now has charge, right? So you'll do as what have been shown in the last 2 examples. Okay, look at the metal. Vanadium is group 5, so it's 5 electron. CO, 6 CO times by 6, we have 12 electrons. But it has negative charge. So negative charge, so you add electron based on the number of the charge. It has one negative charge, so we add one electron. So total up become 18 electron. So it's also obey the Ian rule. Right. Now next example again with the positive charge. Yeah. The same method, manganese is group 7, so 7 electron, CO2 times by 6, so 12 electron, but now it has positive charge. So positive charge we have to deduct. So one positive charge means we have to deduct one electron. So in the end, the total still come to 18 electron. Alright? Okay. Yeah. Now we have a dinuclear. For dinuclear, it's rather different. Yeah, because now we have two metal in it, but the way we count is still the same. Alright? Yeah. Here you can basically do it individually. So this is basically the structure. So we can do it for individual metal. So this is the example. So manganese is 7, group 7. CO is 5. Why is it 5? In total we have 10. We have to divide by 2 because we have two metals. So 5 times 2, 10. And then manganese and manganese, the MM bond we need to consider because it's also contribute electron to the metal. We only take one because basically it has two. But since we have two metal, we split half. So one will get 1 electron, then you add up, it becomes 18 electron. Or you can do it as a whole. You don't need to split it up. Yeah. If you want to do it overall, so manganese 7, but we have 2 manganese, so it's 14. CO we get 10, so you have to multiply by 2, so become 20. But don't forget about the manganese bond. So become 2 electron. So total become 36. Since we have 2 manganese, so you divide by 2, so each manganese will have 18 electron. So you can do it as a whole. Yeah? If it's 3, the same, similar, you can do it individually or you can do it as a whole. But you must be very sure on the types of MM bond that involve. So for 3 metal, the 3 metal is basically bonded through this way. So we have 3 MM bond, that's why we have 6 over here. Then the total should be 54. So 54 you divide by 3, it becomes 18 electron. You do it individually, still okay. Okay. Split for Fe is group 8, CO, each CO having 4, because originally we have 12, you have to divide it by 3, so each Fe will get 4. So 8 and the 2 Fe bond, yeah, 1 and 2. So it's 2 electron, then you total up, become 18 electron. Alright? This another example where we involve what we call a bridging CO. Yeah, a bridging CO. This one also we can do it individually. Yeah, for example, this CO is in group 9. Each one has 3 CO, terminal CO. So become 6, and it has a bridge CO. This is bridge CO. So it will contribute 1 electron each for each metal. So we have 2 bridge CO become 2, and the CO bond become 1, then you add up, everything become 18 electron as well. So this is a bit different because it involves the bridging CO. But we all know CO contribute 2, but since it link 2 metal, so the 2 electron we just split into 1 to each. Right? So lastly, yeah, to summarize what I've shown, yeah, all the examples, in order for you to count the number of electrons on M in metal complex, you just need 2 things. One, you must know how much is being contributed by M, and also how many will be contributed by ligands. Knowing that, you will be able to count the number of electrons on M in metal complex. Thank you.